So welcome back, students. This is the last lecture of 204 series. In the previous lecture, we started with feedback. Now, in today's lecture, I'm going to show you various topologies of feedback and what feedback does to your closed loop gain as well as your input and output impedance. I'm going to teach you some tricks to quickly recognize how the feedback is in any given circuit, and then you can tell if the input impedance or output impedance is going to go up or down. So with those tricks, you should be able to manage any complex circuit with a feedback. Unfortunately, we don't have as much time due to this shortened semester to go through various examples. I would advise you to go through the textbook to look at the various examples. At the end, we will come back to a point where it will all start making sense. Our goal has been to design a very high gain op amp. And when you design a high gain op amp, you have to put multiple gain stages together. And when we put multiple gain stages together, then what will happen is you will have multiple poles in the system. And with multiple poles in the system, when we put a feedback around it, you can get into a situation where the system can become unstable. And I'm going to end this course with how do you figure out if a particular system is stable or not, and then how do you make sure that your system is stable. For the advanced lectures, you can, if you would like to study this further, this material further, you can always register for CMOS analog circuit design, which is a PG level class. Also, there is a mixed signal design class, RF design class. These are all advanced classes which will help you build on the foundation we have done so far. Thank you. So today we are going to conclude the feedback topic. I'm going to go through various feedback topologies. The first topology we're going to discuss is called voltage feedback. And the thing about feedback topologies is the nomenclature can be confusing. And I can introduce you with both the nomenclatures, but then one is kind of different compared to the other. So let's stick to one nomenclature for the purpose of the classroom discussion. I have also given you alternate nomenclature in my notes, so you can follow that when you're reading the notes. So the key part of this nomenclature business comes from, we have a feedback. This is our feed forward gain, and then we have feedback beta gain and A forward like this, right? So this is our output sense, and this is our input return. And the different configurations are based on, is the output current or voltage sensed, and or the feedback voltage or current returned at the input. And that's what defines these different feedback topologies. They have different outcome when it comes to impedances. So we are going to go through one example in detail, and I'm going to briefly introduce you to other examples, the other topologies. So in this case, when we say voltage feedback, the first term is output. So when I say voltage feedback, that means the first term is the output voltage is sensed, and then at the input we are returning a voltage. It will become clear once I draw the block diagram. The block diagram looks like this. So we have a voltage amplifier. Okay, so if you look at this picture now, we have a voltage amplifier A0, which has Vi as input and V out as output. We are sensing the output voltage and applying a beta feedback factor, and then the output voltage from the feedback block, Vf, is subtracted from the input voltage, Vn, to give this effective input voltage at the amplifier input. So clearly you can see we are sensing the output voltage. So hence the first term voltage. The second term voltage is coming from returning at the input, which is also voltage. Now let's look at the properties of this block. Obviously, you have already looked at this before. V out divided by V in is given by A0. That's the open loop gain of the block plus 1 plus beta A0. The key purpose of introducing these various configurations is the input and output impedance calculations are very different depending upon what you do. So first we will do input impedance calculation. So let me draw the schematic for input impedance calculation. So here what we can say is this is my input voltage plus minus V in. And then here is the voltage difference that we are doing. This is the feedback, VF coming out of the feedback factor. And this is going to go in our amplifier right here, which has Rin, and the output will be similarly plus minus A0 V in, and this is your R out. And here is a beta factor, feedback factor, which takes the output voltage and gives you a multiplied version to subtract at the input. So Rin is the input impedance of the original amplifier A0, which we were talking about, this A0 amplifier. Now we will see what happens to input impedance with feedback. Since we have series connection at the input, whatever current I in is going in will go here, since it's a series voltage connection. Other assumption we are doing here is that this feedback network is ideal and it's not loading the output branch. If you remember in the previous examples, the resistance R1 and R2, they were large so that they don't modify the gain of the amplifier by themselves. So in this case, we can write the equations as follows, and then let's focus on the final result. So this is our VF, and V in minus what is VF? VF is let's modify this V in here with VI so that it's not confusing. Okay, so once you get this equation, we can collect the terms together and figure out what is V in divided by I in, and that is going to be equal to R in 1 plus A0 beta. So what Rin is represented as input impedance without the feedback for the original amplifier. And after applying the voltage feedback, what we see is, so the input impedance has gone up by the factor 1 plus A0 beta. So if A0 beta is large, then we can say that the input impedance has gone up by A0 beta factor. Similarly, you can do output impedance calculation. And there what you would do then is, I'm just going to draw the schematic for you. When you're doing the output impedance calculation, you would ground the input and then you apply a test input at the output so that we can figure out how much current is going in the block. And that would be your output resistance or impedance. So here we apply a test voltage source at the output, Vx, and then we try to measure what is the Ix going in. So Ix is equal to the voltage Vx will be at this point. So Vx minus A0 Vi and divided by R out. And Vi is given by beta times Vx and the negative sign because we are subtracting at the input, and the result will be Ix is equal to Vx plus A0 beta Vx divided by R out. So this will give you Vx divided by Ix, which is the effective output impedance with feedback, which is 1 plus A0 beta. So the output impedance in case of voltage feedback will drop by this factor 1 plus A0 beta. So we also say that this goes down by A0 beta factor, assuming A0 beta is very large. Quick circuit example where you can apply this would be a simple circuit. Let me draw it so that you can see. Again, you should know how to figure out the positive and negative inputs. In this particular case, from gate of M2 to the output, there is an inversion, right? So this would be your negative input and this would be your positive input of the amplifier. So this would look like this, a simple amplifier with plus minus, and this is your V out. And now we will put out a resistor divider here, which is like this. This is R1, R2, and we connect the feedback like this. So this would look like this, R1, R2, and negative input connected to the feedback. So we have negative feedback. So here is our V input applied, which is V input over here. So in this case, what is my A0? A0 is given by the GM of the NMOS input pair, GMN, and at the output node, we have, looking up, we have Rout P, and looking down, we have Rout N. So GMN times RON parallel of ROP. So this would be your gain of the amplifier A0. The feedback factor beta is given by R2 divided by R1 plus R2, which is the voltage divider effect. So this would be returning feedback over here. Looking at this, you can tell that it's a voltage feedback. Our final expression for V out divided by V in, you can say that that will be A0 divided by 1 plus A0 beta, and that would be GMN times RON parallel ROP divided by 1 plus R2 divided by R1 plus R2 times GMN and RO parallel ROP. So if this part of the expression is very large, which would be highly likely because GM out, that kind of number is very large, right? So for practical values, this will almost look like 1 plus R1 divided by R2, which is again, reciprocal of beta that we have already talked about. Now I'm going to do overview of other types of feedback where we will change the output or input type of feedback, and then we will just draw the block diagram level pictures right now, and then we will comment on the input versus output impedance with feedback. So the next feedback we are going to talk about is voltage current feedback. As I said again, what this means that is the first term is the output sense and the second term is input return. This signifies that we have a amplifier, and since we are sensing the output voltage, we have plus minus V out like this, and then this is going into our feedback factor beta. So here is the output sense voltage, and then at the input we are saying it's the current feedback. So what this means is that our block has input current and output voltage. So this is like a trans resistance amplifier. Okay, so input current, which means that I have a current source, signal current source I in, which is being applied over here. Since my feedback coming in is also current, then we can connect it like this. So part of the current is being stolen by the feedback factor here like this, and then the final current, error current, which is IE that's going in. So in this particular case, what you would see is a V out divided by I in. Originally, it would have been R out, and now it will be 1 plus beta times R out, something like that. In the voltage case, we had A0. In the trans resistance amplifier, it will be the R out of the amplifier. Now, in this case, what will happen to the input impedance with feedback? So the input, let's say the input impedance without feedback was, let's say, Rin, which is looking into this block was Rin. Then after the feedback, this is going to drop down by factor 1 plus beta R0. And the output impedance with feedback, let's say it was R out before the feedback, that will also go down by beta times R out. Now you may wonder, how do I remember all these things? Does it get multiplied or divided, right? So I'll teach you a quick trick. Essentially, whenever there is something in parallel at the either output port or input port. So for example, in this particular case, if we look here, we have something, the sensing is happening by tapping off the voltage, right? So it's across the output, so it's in parallel. And whenever something is going on in parallel, then we say that resistance output parameter will go down by the feedback. This whole factor 1 plus beta times R out here. Similarly, at the input also you see that there is a current being summed in, so something is the connection, if you will, it's parallel connection. So whenever you see a parallel connection, then that particular input impedance will reduce by 1 plus beta times AR or whatever parameter. All right. In the previous case, if you will, let me compare that with you so that you see. In the previous case, you can quickly tell now that, hey, at the input, I have something going on in series. So input impedance will go up by 1 plus beta A0 factor. At the output, I have something going on in parallel. So then we can just quickly looking at it, we can say output impedance will go down by 1 plus A0 beta factor. So this is like a quick way to tell just by observing the connections what happens to the impedances after feedback. Otherwise, it can become very painful every time write down the equations and figure out is my input resistance going up or input impedance going up or down, output impedance going up or down. So this is a trick that I'm teaching you. The next configuration is called current, voltage, feedback. Again, current is output sense and voltage is input return. That's the syntax. So here is our block, and we are supposed to get current out because that's what we are sensing here, and part of the current is being returned to our feedback block. So we are saying that, hey, this is my I out for my block, and then I'm going to feed that current back into the feedback network, and then I'm going to return input voltage. So since I'm returning an input voltage, I will have to put that voltage in series. So it would look like this. Since I am returning input voltage, this return voltage will be VF feedback, and this is V in, this is plus minus VI. Now, if you look at the original amplifier, we have input voltage and we have output current. Immediately you can tell this is a transconductance amplifier, GM. So if I didn't have feedback, then my transfer function would have been I out divided by V in would have been GM, which is a transconductance. And with feedback, this is going to get modified to 1 plus beta GM. Now remember that the units of beta will keep changing as we go through various types of feedback. If it's voltage, then the feedback factor beta does not have any units, but then otherwise we will have different units because beta GM or beta whatever it is has to be unitless. So in this case, let's use our intuition that I just taught you a few minutes ago. What is going on at the output? At the output, as it looks like, things are in series. So whenever things are in series, what happens to our output impedance, it should go up. Similarly, at the input, also we see things are in series. There are two series blocks connected, so input impedance will also go up, and that's exactly what happens. So input impedance with feedback will be equal to Rn times 1 plus beta Gm. And similarly, output impedance with feedback is equal to Rout 1 plus beta Gm. So whereas Rn and Rout are the input resistance and output resistance of this Gm block. Again, the beta will have units of resistance, so that R times Gm will just give you a number. Now let's look at the last configuration, which is current feedback. Now the first current is about output sense, and the second current is about input return. So keep that in mind. Since we are we are sensing the output current, you will see a series connection at the output, right? So here is our feedback return path here. This is the feedback factor, and this is going to be AI. I'll explain what that means. And the output coming out of the feedback factor is going to be a current. So we have to subtract the currents here, and we will have input, which is I in, and so the feedback IF comes out like this, and here is our IE, and here is your I out. So I out divided by I in case of, so this is a current amplifier, so you will have some kind of AI factor, which is the current gain, and with feedback, this transfer function will modify to 1 plus beta times AI. Again, AI is the current gain, so current divided by current, so it will be unitless. Hence, beta in this case will be also a unitless quantity. And I want to give you, you can pause the video and try to guess what will happen to input impedance with feedback and output impedance with feedback. So when we look at the input, we see things are in parallel. So input impedance with feedback should reduce by 1 plus beta AI factor, purely because things look like they're in parallel. At the output, we see things are in series. Over here, you see that the things are in series. There is a series connection, and here you see things are connected in parallel. So at the input, we see the with feedback, the input impedance will go down by 1 plus beta AI factor. And at the output, since the connection is in series, it will go up by factor 1 plus. Unfortunately, we don't have time to go through all the examples, circuit examples for different cases, but I'll leave that for you as additional reading material, and you can look at both of the textbooks, and you will find plenty of examples where you can look at a schematic, and then you can kind of figure out what kind of feedback we are having there. And once you know what kind of feedback, then you can use these rule of thumbs that I have taught you to see what will happen to input impedance, what will happen to output impedance with feedback. And that's what we are interested in all the time. In the beginning, when we started with feedback, I talked about a word about stability. So we know that when the loop gain is equal to 1, and when the angle of the loop gain is minus 180 degrees, then we have a problem, right? We will have oscillations because of positive feedback. So we always want to stay away from that point. And I'm going to introduce one new term called phase margin. So let's understand what this term is. So we are going to talk about stability. So the term for for oscillations, the Barkhausen criteria, what we had talked about earlier was beta times A of S. If that becomes equal to 1, and angle beta A of S is equal to minus 180 degrees. And when that happens, then the signals will add constructively around the loop, which is from here to here. And we have second inversion over here. So 180 degrees phase shift around the loop plus another 180 degrees phase shift, so which is 360 degrees, which means that the two signals are in the loop are going in phase and they're adding constructively, as a result of which you have positive feedback, and then it leads to oscillation. So when it comes to stability, we want to stay away from this condition, which is given over here. And how far you're from that condition is what we like to call as the phase margin. For stability of the closed loop systems, at the point where beta times A of S mod of that is equal to 1, which is 0 dB loop gain, at that condition, we would like to make sure that beta times A of S angle is greater than minus 180 degrees. Okay, we know for sure that at minus 180 degrees we have oscillations. So we would like it to be greater than minus 180 degrees. And how far are you from this condition is what we call it as a phase margin, and it's referred to in degrees. So this is used to measure phase margin. So let's say beta times AS is equal to angle of beta times AS is equal to let's say 120 degrees, minus 120 degrees at beta times AS equal to 1 at that frequency. Then we say that, hey, I have a 60 degree phase margin. So let's take one example and then things will become very clear. So one quick example we're going to go through is a one pole amplifier. So in a one pole amplifier, we know A of S is equal to A0 divided by 1 plus S divided by omega P1. So in this case, the closed loop response, which is Y of S divided by X of S, will be. So this is something that we have already done before. Every time to do the closed loop transfer function and figuring out if this is okay or not okay is very painful. What we would like to do though is we would like to look at the loop gain. Okay, so loop gain is given by beta times A of S. Okay, and we would like to observe the body plot of the loop gain. And then be able to tell, hey, is this going to be stable or not stable when I put it in the feedback loop, which is kind of what we did if you remember in the previous case. So here in this case, when we defined all these things, we are only talking about the loop gain. The loop gain is beta times A of S. And what our stability criteria is telling us is that when beta times A of S is equal to 1, or when beta times A of S hits unity gain frequency, at that time, the phase of beta times A of S should be greater than minus 180 degrees. That's our desire. Okay, and then we can tell that we are stable. So in this particular example that I have taken of a one pole example, what would beta times A of S look like, body plot? So I'm going to draw that and then it will become very clear. So we are plotting body plot of beta times A of S. You are actually doing 20 log of mod of beta times A of j omega. That's what and on the x-axis here we have is omega frequency. So from the body plot we know that it's going to look like this because it's a one pole system, beta times A of S. It should look like this, and this would be our original frequency, first pole frequency of omega p1, and this is where we hit 0 dB when we cross the x-axis. And if you remember in the body plots, we also know how to plot the phase. Phase would be, we will start with 0. So this would be at the omega p1, this should be minus 45. This is 0 and this is minus 90 degrees. So this is what the response is going to look like for a single pole system. And then you can draw the line for minus 180 degrees. This is right here. And what we are saying is if you look at the unity gain frequency, which is over here for the loop gain, and then we can see that, hey, I have 90 degrees of margin from minus 180 degrees. If at this point, which is the unity gain point of the loop gain beta times A of S, if we had minus 180 degrees of phase shift, then we were in deep trouble, because then we would have had oscillations. And what we are saying is that with one pole system, my phase at unity gain frequency is minus 90 degrees. You have learned how to do the body plots, and I'm only telling you from that. So what I'm saying is that then this is 90 degrees is my phase margin. Okay, so this would be a very stable system. So this would be unconditionally stable, because 90 degrees phase margin is good. What we generally like to do as designers is we would like to keep our phase margin greater than 50 degrees. If you can get 60 degrees, then that's great. But if under all process temperature variations and voltage, supply voltage variation, if you can keep it above 50 degrees, then we have a reasonably very good confidence that your closed loop system will be stable. Let's take an example of a two-pole system. So when I have a two-pole system, so my amplifier will look like this. AS will be equal to A0 divided by 1 plus S divided by omega P1, 1 plus S divided by omega P2. Now let's draw body plots for our loop gain. 20 log of loop gain is going to look like this. Let's say this is the location. So this is my first pole, omega P1, and this is my second pole, omega P2. So this would be your 20 dB per decade, and this is another 20 dB per decade, so this would be 40 dB per decade. So minus, minus. This is all the things that you learned from body plot lecture, okay? And this would be your frequency in the log scale. Now, if we plot the phase for our loop, then it's going to look like this. So first pole is right here, and the second pole is right here. So the first pole, we are going to go from, use a different color. So this is 0, this would be minus 90, and this would be minus 180 degrees. So for definition of phase margin, what we are looking for is, this is my UGF, unity gain frequency for the loop gain, and at that frequency, what is my phase? So in this case, what we are seeing is the phase of the loop gain is close to minus 90 degrees, and this would be my phase margin, which will be also 90 degrees. So this is good. The reason this is good is because this omega P2 is far away from the unity gain frequency out there. Now imagine if this omega P2 starts moving close to unity gain frequency. Then what will happen is you will start getting this, something like this will start happening. And now clearly you can see the phase margin will stop dropping as the pole location, which is omega P2, starts moving close to unity gain frequency. So when omega P2 is right on top of the unity gain frequency location, then it will be 45 degrees of phase margin, because you will have another 45 degrees of phase shift due to the omega P2, and you will have only 45 degrees of phase margin. Okay, and as I said earlier, we want to make sure that our phase margin is it's kind of greater than 50 degrees at least for stability. Generally, as a design practice, we like to keep phase margin equal to 60 degrees for flat, maximally flat closed loop gain, and the phase margin, if it's equal to 70 degrees, then we can get a really fast settling response. That's a little bit more advanced material I'm telling you. So why am I telling you all these things? Okay, if you remember, when we were doing op amps, right, when we just did a simple one stage op amp, which is GM R out, type of amplifier. We get some gain and we get just one output pole, which would be the single pole amplifier, and it's unconditionally stable. Now, to get more and more gain, we like to put more GM out stages in cascade so that we can get more gain. Unfortunately, when we try to get more and more gain, you have multiple poles. For example, this stage will have a pole here, and the second stage will have the second pole, and both these poles, they may not be far away from each other, and as a result of which, just putting two GMR out stages next to each other, you will inherit two poles which could be close to each other, which will result in a unstable system, as we just looked at it right now. So there is a complete field of compensation, frequency compensation, that you can learn, where you can move these poles around using smart techniques. And that's the discussion we generally follow up in advanced analog classes, so that we can create these amplifiers which are really stable no matter what the process temperature or supply voltage variations happen. And that would complete your knowledge in terms of how to design these operational amplifiers, and these same techniques you will use in design of other complex analog blocks. So with that, I would like to end this lecture, and this is your last summation point of EE204. Hope you enjoyed this content. Thank you very much.